welcome to another Objective 9 practice, an Objective 9 problem where we're going to be focusing on the properties of a original function f of x given information about its derivative and how do we use that information to determine increase, decrease, all those fun properties. Now, the thing that's different about this problem, you'll notice, is the derivative graph that we've been given, right? They're giving us f prime of x. They're also telling us that the original function is continuous. See, that information we need to keep our eyes peeled for, because if we know the original function is continuous, it means it doesn't have any holes, no vertical asymptotes, nothing like that. But when we look at our derivative graph, hopefully it jumps out at you. You say, wait a second, we have a vertical asymptote here at -1, and we have a vertical asymptote here at 2. So the derivative graph is discontinuous, but we know the original function was continuous. What does that mean? Well, we should have seen some of these in notes. Maybe, for example, the cubed root function, I believe, is in the notes, where you say, okay, the domain of a cubed root is -infinity to infinity. I can sub in any value I want, not a problem. But the derivative of this, right, would be x to 1/3 x. There we go. Raised to the -2/3. And if I just do a quick little rewrite, we say drop this down to the denominator. And we say, wait a second, now I can't sub in 0 anymore because 0 would be undefined since the function is now in the denominator. And we learned that there's two ways we get critical numbers. One of them is when your derivative is equal to 0. You set your derivative equal to 0 and solve. The other way is when you have a domain change between the first and second derivative, right? So we know we have some critical numbers here. We know these vertical asymptotes are not really vertical asymptotes in our original f of x function. I don't know what the function is, but I know it is continuous. So when we're going to go ahead and draw our first derivative number line, so we don't confuse ourselves by looking at the more busy graph, we are plotting all of the critical numbers. So that's where it's zeros and domain changes. So, and then of course we would put discontinuities as well, but it was continuous, so there's no discontinuities. So we know we have a number we need to keep track of here at -1. Notice it's a dot, not a vertical asymptote, because it is a critical number. We're going to focus on if there's a change, it's a max or a min. Okay, it's not undefined for the original function f of x. Now over here at 2, once again, another dot. And then we're going to look for any zeros. It looks like we have a 0. I'm going to zoom in just a smidge just to see if I can catch that number a little cleaner. Sorry, it's a little blurry, but let's see. It's 1, 2. That looks like 3. So we're going to go ahead and put another 0 here at 3. Okay, another critical number at 3. Now, what we're saying is, what are the y values of my first derivative graph, right? We've already plotted the zeros. Now let's plot the y's. So in this first section of our graph, let me grab my highlighter, put it back to yellow. There we go. This first section of the graph, whoops, when I'm going from -infinity to -1, we can see those y values are all negative. Then let me put that back. I hit the delete button. There we go. Now the next section of my graph, between -1 and 2, those y values are all positive. Then the next section of my graph, between 2 and 3, we can see those values are all negative. And then finally, the values after 3, those y values are all positive. This is going to be enough for us to answer any first derivative questions. So let's go through and see which problems are first derivative questions. They're asking us about where is f of x, not f prime, but f. Where's our original function f increasing? Well, we know if a graph's increasing, it means its slope is positive. The derivative is slope. So I'm just looking for where is my derivative positive? Well, we're positive from -1 to 2 and 3 to infinity. Yay. All right. Next, where is my graph decreasing? Where is f of x decreasing? Well, that means we didn't have positive slopes. That means we have negative slopes. So where is that negative? Well, -infinity to -1 and 2 to 3. Fantastic. So What other information do we need to use the first derivative number line for? Well, that's where we can find our relative mins and relative maxes. All right, so we read our slopes. They will tell us if what we have. So if our slopes tell us we're going down, then up, right? If our graph was original f of x was going down, then up, then you'd see we have a minimum. Here, if we were going from up to down, you'd see there we have a maximum. And then finally, we were going down to up at 3. So once again, right there is a minimum. So where do we have relative maximums? Well, we only had one of them, and that was at the x value of 2. Where do we have relative minimums? We had one of them at x equals -1 and an additional one at 3. And of course, you can write it either as a separated a list, or you could write it as a comma separated list, or you could write it as two separate values. In more, typically, we have you type it in that way. Okay, so mins, maxes, fantastic. So the next question, concave down, shoot. Okay, now this is concave down. Concavity does not talk about the first derivative. Concavity and inflection points, oh, there it is. Those are second derivative questions. One of them, again, is talking about the intervals. One of them is talking about the actual values where you're equal to 0 or you have a critical number. So we're going to have to go back, and essentially all of those are second derivative questions. So we can say goodbye to that number line. We are done with it. There's nothing left. So we will just pop right over back here to our graph, and we're going to say, let's draw a second derivative number line. Remember, this is just a graph of the second derivative function, just where we take away the y values. So the only thing we're seeing here is really kind of like where the y value is equal to 0. We plop that on this number line, and then instead of actually plotting with an y-axis and showing a graph like whatever it would do, we're just saying like, look, the values are positive here, negative here, right? So we're looking for our zeros. Now, how do I look at the f prime? How do I look at the derivative graph and get its derivative? Welcome back to objective 4, right? Welcome back to seeing the derivative graphically. Well, hopefully we learned that the derivative of a function is the slope of its tangent line. So really truthfully, we're just looking at any point in the graph and saying, what kinds of slopes do we have? So you can see that area in yellow I just highlighted. We can see hopefully we see they're all negative. So let's keep our eyes peeled for zeros. Where do we have slopes that are 0? Well, it looks like we have one right here, right? Mins and maxes are going to be the place where our slope is equal to 0, or where our graph just flattens out, right? That again, right, something like that would be a slope equal to 0. So it looks like right here at 1, we have a slope that's equal to 0. Looks to me like at 5, if you look carefully, it looks, I mean, clearly the graph was going up because we went through the x-axis and then kind of went up, and then clearly we're getting back closer to the x-axis. So there is some point in here. It's your judgment call. We know when you're looking at graphs, it's not going to be perfect. So just try to get as close as you can and don't stress. As long as it's close, you'll be fine. So it looks like somewhere right around 5 to me. Again, we have a slope that's equal to 0. So what's going on our number line? The number 1 and the number 5. And that's the most common mistake, because we say, what about the vertical asymptotes? Well, they were on the first derivative number line. No. Remember, those are still critical numbers. Those are values we need to check. So where else did we have our vertical asymptotes? We had one at -1, and we had another one at 2. Right, so we have a vertical asymptote at -1. We had a 0 at 1. We have a vertical asymptote at 2, and another 0 at 5. So you can see, right, vertical asymptote, 0, vertical asymptote, 0. So we have 4 points on our graph, 4 points on our number line. Perfect. Now we just read the slopes. We read the slopes. So let's go ahead here and highlight. We say, what kinds of slopes do I have in my first region here between -infinity and -1? My slopes were all negative. Then in my next region, going from -1 to 1, going from -1 to the x value of 1, I just highlighted in green, this area right here. What slopes do we have? Well, those are all still negative. Okay. Then going our next region from 1 to 2, that area right there, we could see our graphs increasing, or you can look at it and say tangent line, our graph is, the slopes would be positive. Fantastic. Let me highlight that so you can see that region. Then our next color, here we go, going from 2 to 5. So that's the x value of 2 to the x value of 5. You can see our graph was going up, it was increasing, and our slopes are all positive. Last but not least, I need one more color. So let me switch to orange. From 5 on, right, that's this area here. Oops, I forgot to highlight my, there we go. Right, the orange area, you can see our graph was going down even so ever so slightly. It was still going down, so our slopes are negative. So let's write our intervals. Now, where do we know our graph was concave down? Well, I know for certain our graph is concave down from negative infinity to negative 1. Now, what was happening at negative 1? I don't know. My derivative graph is undefined, right? So at that point, I'm uncertain. So we're going to go ahead and say I have to break up my interval there at negative 1, and then I pick back up to get my next area region where I'm concave down, my next interval. So that'd be going from negative 1 to 1. Because we are looking for where our second derivative is negative, right? So we go through and we say from negative infinity to negative 1, negative, negative 1 to 1, negative, 1 to 2, nope, positive, 2 to 5, nope, positive, and then, oh, there's one more, 5 to infinity, that is a negative interval, so therefore we are concave down. All right, so that was concave down, on to concave up. All right, where are we concave up? Well, that means our interval was positive. So where did that occur? From 1 to 2, and 2 to 5. Those would be my two intervals. Fantastic. So last but not least, how do I get an inflection point? What am I looking for an inflection point? Well, I'm looking for where I had a change in my slope. So where I went from negative to positive or positive to negative. So we look at each of our points and we say, did something change? Look to the left, look to the right. You're like, no change. It was negative and it was negative and it was negative. No change. No inflection point. All right, let's check 1. Negative and positive. There was a change, so it goes in our list. X equals 1. That X value has an inflection point. Okay, let's check our next one. All right, checking 2. To the left, to the right, they're both positive. No change, no inflection. All right, you don't count. Next one, let's check 5. To the left, to the right, we had positive, we had negative. Ha ha ha. So there's another inflection point because there was a change. So the kind of neat thing about this is you can have inflection points that come from vertical asymptotes. You could have mins and maxes that come from vertical asymptotes because they're not really vertical asymptotes because they told us the original problem was continuous. So you'll be on the lookout for this. Very, very similar problems. Maybe something that looks like this. I have to be careful. Actually, I'm going to be a little more careful with how I just drew it. Something like this. I'm going to make that an open circle. Something like this. So if this was our derivative graph, sorry, I was making that one up as I went. If this was our derivative graph, regardless if there's a closed dot or not, what I want you thinking about is the number line. What would you see? Right? Well, we have a discontinuity. As long as they told us f of x, the original function, is continuous, right? We need that part. If you know the original function is continuous, you're saying this is a discontinuity, just like an ordered pair, or just like a vertical asymptote. So therefore, whatever that x value is, that's going on my number line. That is a critical number because we have a discontinuity where the original function wasn't discontinuous. Okay, I hope this makes sense, and I hope it makes something that looks pretty complicated and scary a lot more simple when we just break it down into number lines.